This I repeat, this is we are just recording my online class with my student, and my student will be asking me some question and I will be replying. Okay, and I will repeat the question before replying so that you can also understand what was the question. Now we are going to we are studying functions. We proceed with this exercise. So we consider the function f of x equal to x times exponential of 2. Let me make it big so that maybe we can all read it easily. F of x equal to x times exponential of 2 over log x. So let's write the function. The function is f of x equal to x times exponential of 2 over the logarithm of x, right? Nice. The first question is find the domains and limits at boundary points. So first question, we need to find the dom f. What is going on here? So dom f, here we have a logarithm and we have a denominator, right? Let's set the logarithmic condition. The logarithmic condition is that the quantity, the stuff inside the logarithm should not be 0. So x should not should be strictly greater than 0, excuse me. Okay, and the denominator should not be 0, and thus the logarithm of x should not be 0. These are the two conditions that we have. Is that clear? Okay, nice. Now given these two conditions, we continue by saying, okay, the first condition say, okay, x should be greater than 0 and there is nothing else to do. We have logarithm of x that should not be equal to 0. We can apply the exponential to both the side, right? If we have the condition is that, the condition is that the logarithm of x should not be 0. So this gives x greater than 0. Now I apply the exponential here and the exponential here, right? It gives us x should not be 1. So these are the two conditions. X should be greater than 0 and x should not be 1. Let's draw the two conditions to get our domain. X should be strictly greater than 0 is from 0 to plus infinity, right? X should not be 1 means all the possible value except 1. Okay, this is 1. You can see that we have the two conditions from 0, which is excluded. 0 is not in the two conditions, right? It is only in one condition. Then also 1 is only in one condition. So from 0 to 1, union 1 to plus infinity, right? So this is the domain of f. Then the next thing we have to do is to find the limits at the boundary points. The boundary points are 0, 1, 1, and plus infinity. So it will be 0, 1 minus, 1 plus, and plus infinity, right? Let's do our limits here. We have the limit when x tends to 0 of f of x. Let's go and substitute. If I substitute, I will get 0 multiplied by the exponential of 1 over minus infinity, because the logarithm of 0, I repeat, is minus infinity, right? Is there any doubt? I repeat that the logarithm of 0 is minus infinity. Okay, it's what I am using here. So it will give you 0 multiplied by exponential of 1 over minus infinity is 0. A number divided by infinity is 0, so it gives 0 multiplied by 1 equal to 0. Then next limit, let me use the blue pen, is the limit of f of x when x tends to 1 minus. It will be 1 multiplied by exponential of, it is 2 over the logarithm of 1 minus, right? Now it is actually 1 multiplied by exponential of 2 divided, what is the logarithm of 1 minus? Fact, because here is the graph of the logarithm, right? You see that 1, this is 1. If I am at the left of 1, at the left means I am here. When I am at the left of 1, the logarithm is negative, so it is coming to 0, but it is 0 minus. At the right it will be 0, 0 plus. So this is 2 over 0 minus, okay, equal to 1 time 2 over 0 minus is minus infinity, right? Exponential of minus infinity is 0. Doubts? Any question? Okay, please excuse me. Okay, now we continue by finding the last limit. Let me cancel this. Okay, the last limit we get is the limit when x tends to minus to 1 plus of f of x will be 1 multiplied by exponential of 2. Now it will be the logarithm of 1 plus, that is 0 plus, okay? So it will be 1 multiplied by plus infinity, that is plus infinity. And finally we have to get the limit when x tends to plus infinity of f of x, that will be plus infinity multiplied by exponential of 2 over infinity. It is plus infinity multiplied by exponential of 0, that is plus infinity. Okay, this solve the limits and the band at this solve for the domain and the limit at the boundary points of the domain. Okay, next question is find the monotonicity interval and minimum and maximum points. Okay, let's make this bigger. Okay. So we need to find the derivative, right? So f prime of x in this case will be equal to what? F prime of x will be equal to, let's go back and see, the function was x exponential, so we'll first get 1 multiplied by exponential of 2 over log of x plus x multiplied by, we need to derive 2 over log of x, right? Hello? The derivative of 2 over log of x, if I take 2 over log of x, the derivative will be, the denominator is log square f, right? And let me cancel and write it better. I repeat that I need the derivative of 2 over log of x. So we want to derive 2 over log of x. The derivative will be this one square, so it will be log square of x multiplied by the 0 times log of x, which is 0, minus the derivative of log of, which is 1 over x multi, so it will be like this. Okay. Is there any doubt? If you want this this derivative here can be written like 2 minus 2 over x log square of x. Okay, so coming back here, we write it like minus 2 over x log square of x, all multiplied by exponential of 2 over log of x. Is all clear? Are you hearing? Okay. Nice. So this is the job. Now we simplified it. So just have f prime of x will be equal to exponential of 2 over log of x plus, look that this x and this x can simplify, and we'll just remain with minus 2 over log square of x plus exponential of 2 over log of x. Now one can directly see that that it's possible to factorize exponential of 2 over log of x. So we give f prime of x equal to exponential of 2 over log of x. Here we remain with 1 plus, here we remain with minus 2 over log square x. We can still write it better. It is exponential of 2 over log of x multiplied by, now look that this is 1 minus 2 over log square of x, right? So going further, we give exponential of 2 over log of x multiplied by log square of x minus 2 over log square of x. Okay, now we can keep the derivative in this form. Why? We keep the derivative in this form because it is factorized, yes or not? This form is the factorized form of the derivative. What means factorized form? It simply means that if I know the sign of this component, know the sign of this component and the sign of this component, I can know the sign of all the derivative, yes or not? So we just study the sign of each component. Now this component is always positive, yes or not? Because it is exponential of some quantity. The same for this, it is the square of something, log square of x. It's always positive. So the only quantity I should care about the sign is this one. Doubts? Okay. So now we proceed by so at the moment, please. Don't know why it is. Okay, so we don't need to, I repeat, we don't need to study the sign of this nor this because they are always positive. We just need to study the sign of this guy. So we write log square of x minus log square of x minus 2. Is that clear? Greater than 0. But studying the sign of this is not that you see, for example, that we can write it like excuse me, I don't know why it's giving me very few space. Okay, so let's first solve this equal to 0. So we want to study this, but let's first solve it equal to 0. So let's first solve log square of x minus 2 equal to 0. it will give you log square of x equal to 2, right? So log of x equal to plus or minus root, yes or not? And thus x, to get x we apply the exponential. X is exponential of root 2, or x is exponential of minus root 2. Is that clear? So the question, this means what? This means that this stuff have two roots. Now we can build our table for the derivative. To build up the table, our table for the derivative, probably it's time to let me use a new page, because it's becoming okay. So we got I repeat that the derivative we got was f prime. The derivative we got was f prime of x equal to exponential of 2 over the log of x multiplied by log square of x minus 2 over log square of x. Okay. we says that this part is always positive, this part is always positive, and we are studying the sign of of this part. In fact, we set log square of x minus 2 equal to 0, and we found that the root are x equal to exponential of minus root 2 and exponential of root 2. Okay, now we build up the table for the derivative as usual. So x, the domain was from 0, then 1, then plus infinity, right? Now exponential of minus root 2, it's somewhere here, and exponential of root 2 is somewhere there. Doubts? Now the components of the derivative are exponential of 1 over log x, that we know 1 over of 2 over log x, I think, right? This was probably 2 over, okay. Then we have another component which is log square of x minus 2. The third component on the denominator, which is just log square of x, right? Nice. Then we have the derivative f prime. Okay, so what can we then divide it in different pieces. I remind you that the function is not differential, it's not defined at 1, so I put 2 bars, the same as at 0, but the function is not defined at 0 too, so I go, okay. So now we start this function here, it's always positive. This one here is always positive. Any doubt? Now to know about this one, I know that it's here it is 0 and here it is 0. I have to take, so I want it is logarithm square of x minus 2, right? So which number can I take in this interval to test? For example, this is which number can I take in this interval to test? Now if you take 1, you will not be able to test, because a minus 1, I mean you can take something similar to this. For example, exponential of minus root 3. Exponential of minus root 3 will be for sure smaller than exponential of minus root 2. Yes or not? So exponential of minus root 3, if you put it inside, it will give you log square of exponential of minus root 3 minus 2, right? But what is exponential of minus root 3? It's root 3. When you do log of exponential of minus root 3. This gives you minus root 3, and you have the square here, so it will give you 3, because if you do minus root 3 square, it gives you doubts. And you will do 3 minus 2, it gives 1, which is a positive number, right? So here it will be positive. Here it will be negative, also here it will be negative, and then it will be positive. To test from here, you can take exponential of minus 1. For testing here, you can take exponential of minus 1. And testing here, you can take exponential of 1. Okay? Then, I repeat, so for the test here, one can take exponential of minus 1. For the test here, one can take exponential of 1. And for the test here, you can take exponential of root 3. But it will give you plus, minus, minus, plus. Okay? So by the end, the derivative is going to be positive. It's going to be positive, negative, negative, and here is. So we will say that f is increasing in. It is increasing in 0 till exponential of minus root 2 and exponential of root 2 till plus infinity, right? And f is decreasing in the exponential of minus root 2 to 1 and 1 to exponential of root 2. Okay? Is there any doubt? Okay. Now we can proceed by doing. We continue the exercise, and in this in order to the next we go back on the PDF to see what is the next question. Okay, first maximum and minimum point. Okay, you can easily see that if we draw we summarize it like drawing the final table of the function. That will be x, this will be f prime, and this will be f. The domain is from 0 to plus infinity. We have exponential of minus root 2, have 1, we have exponential of root 2. We have that the derivative is positive, negative, negative, positive. So the function here, the limit at 0 was we did it somewhere. The limit at 0 was let me get it. Okay, in fact it is here. Yes, the limit at 0 was 0. Now let me go back to our table, to the table. So the limit at 0 was 0. Then we need to do f of exponential of minus root 2. If you put exponential minus root 2 in the function, it will give you the function is here, so it will give you minus root 2. Let me put the function here so that you can see. It will give you minus root 2 multiplied by exponential of 2 over the log. No, I mean it will give you exponential of minus root 2 for x multiplied by exponential of 2 over the logarithm of exponential of minus root 2, right? So it will give you something like logarithm of exponential minus root 2 is minus root 2. So 2 over minus root 2 give you 2 over minus root 2 give you minus root 2. So you get exponential of minus root 2 multiplied by exponential of minus, which is exponential of minus 2 root 2. So at the end you get here exponential of minus 2 root 2. The function increased from 0 to exponential of minus 2 root 2. Then remember that the function was not defined at 1, so we put 2 bar. And the limit from the left of 1 was something. It was 0, right? The limit when x tends to 1 minus was 0, right? Then we continue by now finding f of root 2. F of root 2 will be exponential of 2 root 2. So this will be exponential of 2 root 2. So probably there is a mistake. There is a mistake somewhere, because how can the function decrease from 0? No. What was the limit here? Excuse me. At the left, I made a mistake. No, there is not a mistake, because I didn't sign the limit here. Please let me make the table more attractive, because it is a bit so. Exponential of root 2. Okay, so I was saying that the limit at 1 plus, we got plus infinity, right? And from plus infinity you decrease to exponential of 2 root 2. And then from exponential of 2 root 2 you increase back to plus in. Is that clear? So one can easily see that this point here is a local maximum, and this one here is a local minimum. Okay, so x equal to exponential of minus root 2 is a local maximum point, and x equal to exponential of root 2 is a local minimum point. Why are we saying we have local minimum? Because the function go local maximum, because the function goes to plus infinity, right? This is just a local maximum. It's not the highest point of the function. I mean this point, and this one is just a local minimum because the function goes lower. The function goes to 0, right? Questions? Okay. Nice. Then draw the qualitative graph of f. So we need to draw the graph. Okay. To draw the graph, I first do the table that we used to do before drawing the graph. So now I repeat that I need to do the graph. So to draw the graph, I need to draw the table in which for each x I put the corresponding y. So we have the points 0, exponential of minus root 2, 1, exponential of root 2, and plus infinity. We have the 0 corresponds to 0, exponential of minus root 2 corresponds to exponential of minus 2 root 2. For 1 we have 1 minus, I mean, yes or not? We have 1 minus, which is 0, and 1 plus, which is plus infinity. From exponential of root 2 we have exponential of 2 root 2, and plus infinity, we have plus infinity. Okay, now we try to draw our function maybe on a new no, we can even use this place. Okay, let's try to draw the function. Okay, no, let me cancel for the simple reason I am cancelling because, by the way, the function has no negative part and no negative x, so I can even draw it like this, just the positive part, right? So this is 0, this is 1, this is let's say that this is exponential of minus root 2, this is exponential of root 2, and so on. Okay, we have the point 0 0, but pay attention that this 0 0 I will open because the function, by the way, is not defined at 0. Okay, we open like this because the function is not defined at 0. Then we have the point exponential of minus root 2, that corresponds to exponential of minus 2 root 2. That's something like, let's suppose that is exponential of minus 2 root 2. Yes or not? Then we have the vertical asymptote at 1, because the function goes to infinity there. We have the point 1 minus corresponds to 0, so we'll open like this. Yes or not? And then 1 plus, so at the left, at the right of 1, the function corresponds to plus infinity, so it will be here, right? And then this point, this exponential of 2 root 2, it will be here. And finally we have infinity, that is here. You can easily see that the function will first increase to this point, then decrease. This corresponds to this. Increase like this corresponds to this part, yes or not? And then it will, after the vertical asymptote, which is 1, it will restart at plus infinity, decrease, then increase like this. Doubts? Okay. Then going back to the exercise, the next question is the next question for this exercise is where is the exercise? Is this here? Oh, okay, it's here. Find a continued prolongation of f on minus infinity 1. Say if there exists a continued prolongation for f on R. Justify the answer. Okay. Okay, so we want to find the continued prolongation of this function in the interval from minus infinity to R. Okay. Finding the continued look, what means finding the continued prolongation of a function in minus infinity to 1? Look, this function, is it defined in the interval from minus infinity to 1? The function, this function is not defined in the interval from minus infinity to 1. Yes or not? This function is not defined in the interval from minus infinity to 1. If you look at it, if you take the interval from minus infinity to 1, the function is not defined here inside. Okay? But it is just defined in the interval from 0 to 1. So we should find some function in the interval, we need to prolongate. It means find some function in the interval from minus infinity to 0 to combine to this one to your function in order to get all the definition in the interval minus infinity to 0 to 1. Is that clear? I repeat, the function is just defined in the interval from 0 to 1, as you can see here, and then from 1 to plus infinity. But the question is that, is there a way to find some function that prolongate this function in the interval from minus infinity to 1? The answer is yes. Why? Because it is sufficient to take any function that at 0 is equal to 0. Because if I take any, let me go back on any other, on another suppose that the graph of my function is like this. The graph was like this. So this is 0, this is exponential of minus root 2, this is 1, and the exponential of, let me make it big, of root 2, and this was plus infinity. We saw that the graph was something like, open here, this was some exponential of minus 2 root 2, and then there was the asymptote, and then this point was a big up. So the function was something like this. I'm just doing a qualitative graph, okay, and like this. Okay, nice. What is the, so look, the question is that, is it possible to find a function that prolongate this function in the interval from minus infinity to 1? Consider, for example, if I just take the function f of x equal to 0 when x is smaller or equal to 0, and f of let's say I'm taking the function g of x. So g of x is equal to 0 when x is smaller or equal to 0, right? And equal to f of x when x is greater than 0. If you draw this function, what will happen to this function? If you draw it, you see that for all x smaller than 0, the function is always 0, right? So it will be like this until 0 included, right? Now from all x greater than 0, we use f of x now. So f of x will continue like this. Put the ball here at 1, and then continue. Yes or not? Now this function is now continue in the interval from minus infinity to 1. Yes or not? Excuse me. This function that I just get, if you look at this function that this g of x is now continue in the interval from minus infinity until 1. You see that yes or not? At 0 there is no more of the problem. So yes, it is possible to find a prolongation of this function in a continued prolongation of this function in the interval minus infinity to 1. But we cannot do that. But it is not possible to do it for r. It's not possible to do it in r. Why we cannot do it in r? Trying to do it in r means, is it possible to find a continued prolongation of this function that is continued at every point? Look, when the function arrives to 1, it goes to infinity. So there is no way. So there is no way to combine another function to this function at 1 in order to make it continuous, because the function goes to infinity. Is that clear? So the answer is yes. I can find the continued prolongation in the interval from minus infinity to 1. And here is an example of continued prolongation. but I cannot find the continued prolongation for all x in R because the function when x tends to 1 goes to infinity. Okay, is that clear? Okay, probably this last question is not that clear for you or for any other body watching this video. If it is the case, maybe you just write me some comments and we turn back on it.